Hello, very good afternoon to all of you. Today we are gathered here for the 8th Computer Engineering Seminar titled Application of Self-Supervised Learning in Natural Language Understanding, Moving Beyond Labeled Data. To conduct the seminar, we have with us today our alumnus, Mr. Shamane. Thank you for sharing your time to be with us today to enlighten us with your knowledge and experience, Mr. Shamane. So before moving forward, let me give you a brief introduction about our speaker. Mr. Shamane is a PhD candidate at the University of Auckland. He has completed his master's at the Bioengineering Institute at the University of Auckland in 2018. He has also worked at Singapore University of Technology in 2017 as a deep learning researcher and also as a senior machine learning engineer in a New Zealand-based startup in 2019. Having both industrial and research-related experience in machine learning and related areas, it's truly a privilege to have you with us today, Mr. Shamane. I hope all participants today will be able to gain the maximum out of this session and use that knowledge fruitfully in the future. Let me invite our speaker, Mr. Shamane Sirivaradhan, to carry on the session.
Yeah, so let me first share my screen, right? I don't know whether I can I? Okay, there's so many tabs, so I need to just, I think this is the one. So I hope you all see it.
Yes, we can, yes.
Okay, perfect. So yeah, I'll go. I kind of do it here. I don't know whether I can kind of here. Yes, all right. Yeah, thanks for that nice introduction first of all. And yeah, I'm Shamane, and so I'm hopefully finally a PhD candidate at the University of Auckland, New Zealand. My lab is called Augmented Human Lab, and I'm supervised by my associate Professor Surangananakar and Professor Mark Billinghurst. First of all, I would really like to thank Dr. Herath for the invitation, because it's been really nice, because to see these pair faces and do something at the University of Peradeniya, although we are like doing this virtually. It's really nice, and I'm really thankful for that. So in this talk, I kind of touch upon some areas I explored during my PhD so far, and yeah, I hope it will be a good one, and you'll get motivated from it somehow, and also get some new knowledge. So I'll kind of go with the topic. Actually, this is my PhD topic. So it's called application of self-supervised learning in natural language understanding, moving beyond labeled data. So that's my my main area of research, I would say. So first of all, I'll kind of go through what is this natural language understanding, or in short term we say NLU. It's like understanding humans or behavioral patterns, or recommending something through text, like or language, right? Specifically language. And it's like this broad area, but mainly there are like few common applications that I have mentioned here. These are like very common. You kind of can see this stuff in your day-to-day mobile phone, Google, and everything. So one thing is emotional recognition. That means like if there's something related to human, let's say some kind of an idea or some kind of a product, related to product, some kind of a message or something. So sometimes you need to recognize what's the emotion in it, or maybe for for these use cases like psychology and stuff, you need to know about emotions, and same as sentiment analysis. Then summarization also a key element, because say it is like nowadays we kind of keep collecting a lot of textual data, and then the problem is we kind of keep collecting, we call it now, there's this information overload. So it would be nice if we can create algorithms that can summarize these large amount of data and help human decision makers to understand what is in there, right? And other most common thing is conversational agents, mainly Apple Siri, Google Voice Assistant, and Alexa. All those things. The core is natural language understanding. So then this is like my main, I would say, like application area. And again, like as we all know, deep neural networks or deep learning has improved the entire field of NLU by a substantial margin. It is kind of pretty much similar to what has happened in computer vision. So yeah, so deep learning is perfect actually, but again, we all know deep learning has this limitation, right? That is you need large amount of labeled data, so that's a problem. And yeah, it's the problem actually. Then sometimes yes, we can collect large amount of labeled data, but it's really hard. Well, first thing is you need expert knowledge to annotate data, and the other thing, main thing, is user privacy. It's going to be the biggest thing in future. Even if you are in Facebook, even if you are in Google, the user privacy will be the main thing, like in future, like concepts like GDPR, these and also you might have seen these Netflix documentaries about these data privacy things. So it's not that easy to annotate millions of data. Of course, you need annotated data to make useful applications, but it's not easy to annotate millions because of these two factors. And so like my main focus is on how I can kind of go through, or like kind of provide a solution for this exact problem. Like there are a lot of NLU problems, natural language understanding problems, but these problems might not have large amount of labeled data. So what's the solution? Can we create intelligent agents or algorithms that can work with small amount of labeled data? So that's like my main focus. Under this, I mainly have explored already like three applications. So first thing is multimodal emotion recognition, and the other thing is automatic summarization. And actually these first two is I'm kind of almost done with them. And the third one is domain specific question answering and search, which is like mainly my current work, like I would say last 1.5 years. And if you like closely look at these three problems or three application areas, a common thing is they do not have large amount of label data. Of course, like again, I just want to highlight this. It's really hard in practical scenarios. You can't just expect an algorithm to learn everything without having labeled data. It's not like that, but it's like at least we need to give some amount of label data to label data for algorithms to show, like to learn and kind of come up with better generalizations. So the thing is, like these three areas, it's not easy to find millions of label data. So that's why I kind of selected these three main applications in my work. And so in order to solve this thing, I'm kind of use a specific paradigm called self-supervised learning. It's I think you might have heard of this concept, self-supervised learning, which is kind of one of the hottest thing happening in the deep area of deep learning, I'd say after 2018. I mean, this is more like an alternative for unsupervised learning. Like, because I mean, you can throw rocks at me, but for me, unsupervised learning never worked. Like, it wasn't progressive enough, because it's really hard. Because it's really hard to kind of going with cluster mechanisms and stuff, and not having any labels or not having any inductive biases. And self-supervised learning was first introduced by the father of the deep learning, Jan LeCun from Facebook, as an alternative to the unsupervised learning mechanism. So again, to summarize this slide, so mainly I selected three topics, which kind of 3NLU topic, where the main problem is not having large amount of label data, and I kind of tried to use this specific technique called self-supervised learning to solve this. So in today's talk, I'll mainly talk about multimodal emotion recognition, because I think it's kind of a good point to start. But if you have anything related to automatic summarization and especially domain-specific question answering and such, please later ping me up. I'm really happy to collaborate. So moving further, I'll first kind of go through what is self-supervised learning. So this is a very broad topic, to be honest, but I'll try to like explain this in layman terms. So again, as I said, self-supervised learning is a representation learning approach. So mainly, you need to create better algorithms that can learn representations of different data modalities. Let's say speech, video, audio, then text. So you have this algorithm, and it kind of can represent these data. So that's the entire idea. The difference is you don't need humans to label this data, because that means you need some kind of labels. I'll come into this exact part later, but that kind of labels you don't need humans. It's not like this is a cat, this is a dog, this is a flower. You don't need humans. You kind of can these models can use naturally available context as labels. I'd say not the models, like the entire concept, right? Entire concept can use that. So in order to kind of give a concrete idea, I have these two figures, left and right. In my left hand, supervised learning workflow is pretty straightforward. Let's say you have some kind of large amount of data, and you ask humans to annotate it with whatever the classes you have here, cat and dog, and then you can use some convolutional neural network which might have trained on some large amount of data prior to this, and then need to fine tune it, right? So we call it transfer learning. This is like the usual supervised learning workflow. But when you come to self-supervised learning, so I'm using this SSL word from here on. When it comes to SSL, it has actually two steps. So the first step is mainly make sure this your model or your neural network knows general things about this exact data modality. Then what you use is you train that big network, and then use that network for your downstreaming task. Downstreaming task means your specific task. So make sure, so the main thing is these tasks are the tasks that you need as an industry, or like, let's say some application scenario. Let's say this might be predicting the sentiments, or kind of predicting the emotion. And the good thing is, since this network now already knows about general representations of that modality, here you don't need large amount of data. That's why you can work with small label data set. So one major thing you need to understand is this, how this first step being done, right? That's something like, because you might be wondering how they kind of train a large neural network without labels. So we call the mechanism, or we call it, like, in theoretically, the inductive feedback, the inductive bias. Actually, the inductive bias comes from this pretext task, right? So I'll explain what this is actually very simple. So we use very simple very simple connections in your own data. But I'll kind of explain these pretext tasks in my next slide. But before moving on to that, just what you need to understand is this step, the first step of self-supervised pretext task learning. It's more like, just imagine like the good example would be, let's say, undergrad student, right? So let's say an undergrad student. So there we do not learn everything that like we learn some basic things about, let's say, engineering, but you kind of can't say you learn specific stuff related to the company that you're going to work for, right? But what happens is, since we have that basic knowledge, once you join that company, you know the project, then you can quickly adapt, right? You don't have to spend 4 years or 3 years, or you don't have to spend hours on lectures to do that part of work. Actually, self-supervised learning is like that. First, you make sure this network knows general structure, general properties of your data, and then then quickly kind of adapt for your specific task. So let's kind of see like what are these pretext tasks. So these pretext tasks are pretty much data model specific. Let's say for vision, there are different pretext tasks. For audio, there are different. For video, there are different. And for text, there are again different tasks. But I kind of selected this like easiest one, text one, because it's really easy for us to understand. So this in this figure, this bird thing is Sesame Street bird. It's like a neural network architecture, which is we call it a bidirectional transformer, which is like the architecture at the moment, pretty much ubiquitous. You kind of use it for vision, speech, and text, all these three main modalities. It's kind of very effective network. So just imagine, this is like, if you don't know about transformers or BERT, just imagine this is like a simple neural network, right? So how they do this training thing, the pretext thing is pretty simple. You first take a sentence, and this sentence say, let's stick to improvisation in this skit, right? So this is the sentence. So maybe you kind of drop some words, like, you know, commas and stuff, but this is the sentence. So what you do is, like, you randomly mask out a word. Here they mask out the word of improvisation, right? So I mean, in order to masking out this thing, you don't need any human. You kind of can run a simple Python program. It's like we randomly mask out this word. Now it's not there anymore. Then feed this sentence with the mask. You kind of use a special token, and then ask the neural network to predict what is that word, right? So basically, these words or the tokens will go through the neural network, and then you use some kind of softmax, just a distribution, probability distribution, and then the probability distribution should correctly predict. I mean, in an ideal scenario, correctly give the most prominent probability for the word improvisation. Of course, it won't give in the beginning, but you have a label, right? You can say the neural network, okay, you need to predict, you need to give high probability to this word. So by this way, you kind of can keep training these models, because you can have billions of text like this, right? Billions of text like this, and they randomly mask 15% of token. This is like a hyperparameter which works nowadays. And then you just keep training this stuff for like good old 3 weeks, 4 weeks, maybe months, I don't know. It's all about how much money you have. So then you have a network which knows about language, right? That's the main thing. So this network might not able to do specific tasks yet, something like sentiment analysis or translation or whatever, but it knows this language structure now, because language is very structural thing, right? Like English is not my mother tongue, but still I know English because I learned from my school, university, and also here I have added some slangs and different words because New Zealand is an English-speaking country. So I know that structure of English, right? So then I might able to even read a book, like I can read a book and also write a poem because I know the language structure. So same theory. So you kind of create this nice graduate student who knows about language pretty well. Then the next step is you use this neural network weights, just plug that weight to your simple PyTorch code, which has a training loop, and then just fine tune on your own task, because then you have a small amount of label data about sentiment analysis. Let's say you just fine tune this, but yeah, that's like that's mainly this first step of the SSL workflow. So before moving forward, I wanted to say one more thing. This step is very expensive because it's been empirically proven if your network get larger, that means if it has more neurons, and then if you have more data, it kind of can give better results, right? So because of that, training this kind of a network nowadays could cost, I'm talking from GPU cost perspective, it would cost from 400k USD to 400k USD to 5 million USD. This is really expensive. You might have heard of this big language model called GPT-3. It kind of, they spent around 5 million, as far as I know, because from OpenAI, they spent $5 million to train this. So it is not that practical to train one of your own if you are a graduate student, even for a company. I don't think it's like very rare, I think. So usually what happens is the big companies like, let's say, Google, Facebook, Amazon, then Alibaba, they have their own, and then what else, like Nvidia,
Microsoft?
Microsoft, yeah, exactly. They have their own. They feed a lot of funding, and then they have their own models, and they open source. They actually open source these weights. So this is actually revolution. This actually, I mean, I would say this has changed the entire field of AI, because also the research, because as a graduate student, if you don't use this kind of a big model nowadays, there's no way you get a publication in, because end of the day, machine learning AI is all about performance, right? Because you make sure your AI works. If it doesn't work, like, it's really hard to move forward from that way. And these models can give you good results. So I mean, you can read it later. We now the trend is called data centric AI, because you have a model now. They're like, it's I mean, practically speaking, it's not that advisable to spend so much time on coming up with some mathematics, and I don't know, it might be good or bad. I have pretty much mixed feelings about it, but the main thing they say is, it's like it's rather than spending so much time on coming up with new architectures and stuff, use these kind of models and try to come up with better ways to use them. So there's this new concept called, we should go away from model centric AI to data centric AI. Data centric AI is all about having a good data set, small good refined data set, because this self-supervised learning actually enables this data centric AI, because you don't need larger amount of data now, right, for a specific task. So these companies or research groups can mainly focus on kind of refining their data sets which could improve the performance end of the day. And so in my work, what I have done is, and what I'm doing is, mainly I use these kind of models, and then try to see what's the best way or the better ways to kind of combine them together, or kind of fine tune them, and get my expected results. So yeah, I just wanted to tell you it because I think it's really important to understand how we should head about it. So yeah, and that's self-supervised learning in a nutshell. But there are so many resources. There's an amazing blog by Facebook, self-supervised learning. It was actually written by Jan LeCun. You should definitely read it. Even like even I got a lot of ideas from it. It's very new, and it's just good. Just you need to Google Facebook research, Facebook blog, Facebook AI blog, self-supervised learning, and yeah, it's really good. So yeah, let's get back to the multimodal emotion recognition. So this is the ground I'm working on. Actually, it's pretty straightforward, honestly, and there's not much hard stuff. If you, in my PhD, if you know what is self-supervised learning, and if you know how to code well with the PyTorch or PyTorch Lightning, this is pretty much it. So yeah, and again, like you train this thing, and then this is like a downstreaming task, right? This is what I have been mentioning for the last couple of minutes. So you have this already trained model, and you have your own task now. You can do it here. I just use this slide. It's about spam detection, because this thing now knows about the language, and it can get fine-tuned pretty easily, right, for this specific task. All right. So I'm going to like so yeah, and the like so as I told you, like the like this network might only for the text, but you can have several network, like different, because people kind of train these kind of networks for speech, vision, audio, video, and then they can represent that modality, right? So I wanted to see how I can use, or how I can fuse these stuff together, and together to get better results. So yeah, but again, that fusion is not trivial. So that was like my main thing in the first research question. And the second research question was, I told you this exact architecture called BERT, because I really like transform architecture. It is like ubiquitous. That means just imagine this, like more like you have, let's say if you're coding, you have this Android open source repo, right? So you can develop things on top of Android. Similar to that, like, because when you have one model, you say, okay, this neural network architecture could be used, or could be used to different data models. It make this entire pipeline very easy, very software engineering friendly. So there's this BERT like means there's this transform architectures, like there's this transform architectures that been pre-trained on speech, vision, and text. So there I was checking if I'm not using any other thing, but if I use only transform architectures that been trained on different modalities, what would be the accuracy, and how I can kind of fuse it together. So yeah, but it's kind of pretty much the same, but you'll understand when I'm explaining. So so first research question, like mainly how can we utilize multimodal SSL features, right? So the approach is pretty simple. You use already trained pre-trained networks. I actually use tri-models here. I use speech. I used vision. That means like a small video clip. So basically the idea is like you have this these data sets, multimodal emotion recognition data sets. They consist of a small clip, let's say 30 seconds something. It has video, audio, and text, and you need to predict basically what's the emotion, right? So happy, sad, anger, something. So so there what I did was I selected 3 pre-trained networks. These been mainly open sourced, trained by this been mainly trained by, this is Facebook. I think this is also, this is CMU or something. So they kind of have open source them. You can find the checkpoints. So how I kind of can, what's the optimal way to combine them and train them to, because no one at that time no one has like done training a model on that only uses SSL representations uh, for the task of multimodal emotion recognition. So that was like my first thing. So I wanted to see like how I can fuse them, right? So this is like this is like the this is like the main idea or the main thing what I have done. So what I did was basically you have this I send my speech stream to through this network called Wave2Vec, and I get speech embeddings. That means it's not a vector, just one vector. It's kind of stream of vectors, because these are representations. These are all vectors. And also I use text, and I use video. Video means in video what we do is we kind of use each frame and send it through a network and get the representation of that frame. So dimension, this is like a vector stream actually. So let's say it might be specifically this speech is like 1024 into 1 into 1024 into your number of time steps, right, which is temporal dimension. So these so we have, but the thing is like none of these features kind of are interconnected before, because people have independently trained this stuff. They might not even know someone would try to fuse them together. So the dimensions are different. So you just can't just plug them in. And also the other thing is, I told you, since pretext training, like pretext task training or self-supervised pre-training is super expensive. You just can't train 3 networks by your own, right? So the entire idea is like how we can use these already available checkpoints to this task. And actually just imagine so I did not just use features. Actually I use the entire networks. I actually fine-tune entire 3 networks because that's the common thing in self-supervised learning. You just don't use features. You can actually use features, but it's better if you fine-tune the entire network. So although I here mention it's speech SSL embeddings, when in the back propagation I kind of propagate gradients throughout the networks. So basically the entire network is updated. So yeah, and then so moving forward, what we do is like you have these speech embeddings and text embeddings and video SSL embeddings, and then we kind of came up with a fusion mechanism to use these embeddings and kind of use these embeddings and get the final result. So yeah, there's a bit of theory and you need a bit of prior knowledge on that. But again, like what we use is we kind of use some a different mechanism called cross attention. But I'm not going to like go through what the theory behind it. But the idea I need to give you guys is like when you are using these kind of networks, independent networks, you need to come up with better mechanisms to fuse them. So that was actually my first research question. You use different mechanisms and kind of make sure it works. So in that process, of course, I might have to add this. Just imagine these are like small neural networks with some layers. something like that. That's like kind of not easy, but yeah, so you kind of need to add a bit more parameters. So yeah, so that was the thing. And again, so this is like I told you, this is like a small neural network. In this neural network, there are some kind of functions happening, like what is this cross attention, self attention, those kind of stuff. So that's like this that's the general idea of this actually. So yeah, again, like the results wise, for the results we kind of uh, you need to, because in deep learning you need to have a standard data set to show your model works, because it's pretty empirical. You can't say this works from any other way, right? So we use like 4 data sets. These are very standard data set, and at that time we were able to like pass the previous state of the art accuracy on all 4 data sets. And some data sets it's been like quite 5%, 6%, quite significant things. And yeah, so also we kind of did an ablation study, like which modality has more I mean, ablation studies, like it's also a must, because in deep learning everything is empirical. You need to see like how different parts of your network works. Only way is like you need to run a lot of studies. Like okay, if I what would be the accuracy if I use only text, only video, only audio? Then what's the accuracy if I use text, video, text, audio, something like that? Then this is like I told you, I use some kind of fusion mechanisms. They also can have different mathematical formulations. So there's like, if I use pre-intermodality attention, what might happen? If I use post intermodality attention, what might happen? So yeah, that's like pretty much standard procedure. So yeah, so end of the day, you need to show is like, okay, I mean, your expected result should be whatever you have done has improved the accuracy. And yeah, so accuracy, and it is like effective enough to make a change. That's what you do here. So yeah, so the summary is like in this research question, so I mean this exact project, I would say is like we introduced this novel SSL embedding fusion mechanism that can change easily, that can be easily used with more than 3 input modalities. And then yeah, and then we kind of show this trimodal SSL features. So main thing we wanted to show is like, when you use SSL features, it's fine, they might be pretty independently trained, but you can still use them together to do a task, which shows the effectiveness of self-supervised learning in a way. And also, yeah, the ablation studies, the things I said. And yeah, so you don't actually, I mean, I don't expect you to like understand every bit and pieces of these things. And also this is like 2019, I would say 2019. Yeah, so there are better methods than this now. It's like pretty much changing, but the idea you need to get through this is, if you can still use these are like, you can still use different SSL models, and you need to come up with better mechanisms to fuse them. And yeah, then you can train them with a small amount of data sets and get a better accuracy, right? So that's the first project. And then the second one I did along this emotion recognition is this thing, like how can we actually, so after this one, I really liked this model BERT, and I saw the effectiveness of the BERT. Yeah, actually this one actually changed also my work and the way I think of self-supervised learning. So so here next what I did was, so previously I told you I used three different networks, and these networks architectures were not the same, right? But uses a transform is like a, just imagine there can be different convolutional neural networks, right? ResNet, then Inception, blah blah blah, then transformers. So in the previous one, actually, because till like those days when I started, we had a transformer model. Transformer means, again, this specific neural architecture only for the text. Then for the audio, we only had, we means like this open source checkpoints, because I told you we can't train things by our own because we don't have enough money. And then for the audio, it was like this network called Wave2Wake, which has built upon temporal convolutions. And for the vision, it was FabNet. So these are completely three different architectures. Their embedding stream is different, and it's everything is different. But then Google, actually Facebook, trained a model called Wave2Wake 2, which is like exactly like this text model, like the transformer, but they train with audio. So I wanted to see if the two networks architectures are similar, is there a better way for me to fuse them? Because the problem here is the main problem here, what I found is, so these networks, the networks I used to extract embeddings are kind of very large, and I had to backpropagate gradients through them, because otherwise the results wasn't that good. I mean, not that good means if you backpropagate throughout all the networks, it improves the results. And then what I'm saying is, altogether number of parameters could go easily about 400 million, like altogether this big networks, 400 million parameters is like, you really need high-end GPUs. Even in the inference, you need a good amount of computational power. And then you can see, like, this is a mess. Like, nobody likes to add a lot more mathematics, because it's really hard to prove. It's not like I don't like mathematics, but it's really, really hard to prove this Hadamard product or this thing works, unless or otherwise you do these empirical evaluations, right? So it would be nice if we can reduce this mess here. It would be nice if we can fuse them easier ways, or because it will make the entire process very seamless. So that was the idea. So since now since we got two networks which kind of similar in architecture, then I wanted to see, like, if what's the best way to fuse them. So yeah, so the BERT-like is like, that's why I use the word BERT-like. How can we optimally fuse BERT-like SSL models for speech emotion recognition? Because at that time only for speech and text we had transformer models, but now you can have video transformers, you can have visual transformers. But yeah, I went along with speech and text, because again, those modalities are the most prominent in emotion recognition when you compare to vision, because non-verbal cues are, I mean, you need them, but still prominent features are always vision and speech and text. So I'll kind of quickly go through what is BERT. I think this is really important, because this is more like the self-supervised learning 101, because of this model only, self-supervised learning got pretty famous around the research community, and it got a lot of media attention, and even Twitter threads and everything. People kind of started to look at self-supervised learning as a very big thing, because of the effectivity of this model. This being introduced by Google in 2018, and it's the same as, like, they use this pre-training which I talk about, masking words. And yeah, it's kind of outperform humans pretty for many tasks, many NLU tasks. And the good thing is, it has this special nice structure. You like this, you have, so it like it kind of, you can have one single vector which could represent the entire sequence, something like that. Then you can have tokens that could kind of differentiate between a sentence fragment, something like that. So the architecture wise, BERT was really good, well maintained, and also it also gave pretty good results. So again, like kind of repeating. So until 2020, researchers had only access to text-based transformer models similar to BERT, right? But then Facebook AI open source pre-trained SSL model similar to BERT, that has trained on discretized speech signals. So basically, you have almost same neural architectures. One is trained on speech, the other one trained on text. So my approach was like, I wanted to jointly fine-tune these BERT-like models. Again, the big question is, what is the best way to fuse it, right? For those emotion recognition tasks. So yeah, that was mainly the research question. And yeah, so yeah, this is actually beautiful. You can see like even the image is not that ugly. So I kind of use a shallow fusion and cross attention fusion. Cross attention fusion was the mechanism that we developed in the other work, I would say. And so shallow fusion is pretty simple. This is like the speech transformer model. This is the text transformer model, because in self-supervised learning, more simpler your method, it's really good, because these networks are already trained. People have spent millions of dollars, so you need to make sure you can use them pretty efficiently without adding a lot of layers, without adding a lot of new parameters, because that's the entire point of SSL, is use a big language model pretty efficiently for your own task. So that's how it works. And so you input the speech signal and you get some kind of stream, right? Some set of tokens, and then you use you input the text and you get some set of tokens. And I told you these architectures have this special qualities, right? Like one quality is like this: we have this vector representation called class, which could aggregate the entire properties of the entire sequence. You get what I'm saying? This is more like this. So you have a sentence, and and there's this vector which kind of combine the knowledge or the idea of that sentence. So this been sum up to 1024 or something, like in dimensions, and you don't need to go through all these vectors. So we call it class token. And then I tried like this simple concatenation, just concatenate these two and send it through a softmax layer and predict what is the motion. So this new thing would add around like 1,000 new parameters. These networks already been trained. You don't have to use a lot of neurons. In the previous one, actually, it was like, I'd say 2 million new neurons, right? 2 million new neurons. More neurons means you might need more data, right? So make sure. We wanted to see like, is there any way that we don't add much more neurons, but still kind of can connect them? So this is that thing. And then cross attention is what I said. You have a lot of that means I let the vector representations to interact with each other a lot. So it's not just this thing, but maybe like intermediate tokens, and you kind of use something called cross attention. Then I use two class tokens and try to predict, right? So basically this has this intermediate thing. So because someone could argue, why would you say this is the optimal one? What if these stuff interact with each other, interact in the sense with learn from each other and move in? What is it like? People could ask, right? So the state, we use another state of the art method. I think this thing added few more millions compared to this. This is like 10,000 or something. I don't actually remember, but the difference is like very large, thousands to millions. So so the results suggested that this one is actually optimal compared to this. Again, proves how good these models can learn representation and how quickly you can kind of fine tune them for your specific task, right? So yeah, again, like we beat our own accuracies also, but main thing I found is how if you move with this self-supervised workflow, how easily you can use them without doing this much more painful processes, right? which kind of make everything nicer. I would say actually self-supervised learning make the AI makes the AI pretty much software friendly also, because these stuff are pretty much, you don't need legacy codes and stuff, like you kind of can create a simple structure for everything. Yeah, so that's actually mainly the work I've been doing. So again, these are results. You can kind of uh, find these papers in my Google Scholar and read it more, but I do not want to go through the theory in this talk, because main thing is these things might be pretty much outperformed now, because things are pretty rapid at the moment. So yeah, so although we have time, I just wanted to talk a bit more about using these pre-trained models, like the challenges also, because of course you have these nice pre-trained models, and what about what are the challenges we have in them, right? So first thing is so because someone could argue, like, why not we also try to pre-train our own models and pre-train our own models and then use it for downstreaming tasks, especially in domain specific thing. So so one thing is, like, they are so I can hear a feedback. Hello. Hello. Can you hear? Can you guys hear me?
Yeah. Now go ahead.
Yeah, I do hear. Yeah. Okay. Sorry. So this paper is like this is from Sales AI tool lab or something. Yeah, AI tool lab. And this paper actually, the cost of training NLP models, it kind of it shows like how uh, these these big networks might cost like 80K to 1.6 million. And then how they kind of this might be some, I mean, this paper is really nice. It kind of talks about not just the tech, but socio-economic things, like how, because researchers all around the world kind of forced to use these big networks, and they kind of create this, the shell, like the technology. Although we think it's open sourcing is good, now it's more like, okay, I need to wait until Facebook open source this checkpoint. Actually, we are doing some projects with Facebook now about virtual reality now, because it's a, of course, now actually have waited like 2 months thinking they rather than trying to do by myself. Actually, luckily they open source a checkpoint after 2 months, and we able to finish the project without writing much codes. So sometimes you need to do it. So this paper is talking about, is it good, is it ethical, is it, what about these new things, what about out of box research. Yes, so those kind of pros and cons. And then again, what they show is like why all these big models outperform these public benchmarks are from big companies like Facebook, Excelnet team, again Microsoft, Baidu. So it's like pretty much this clash of titans kind of a thing. That's what they say, because end of the day in AI, performance matters. I mean, it's the reality, right? Everyone needs to use an algorithm which gives at least even if it is 1% better, you go for it, right? That's the entire point. So this is like that thing. And I talked you about GPT-3. They kind of 12 to 5 million. This is 12 million is not just GPU cost, the researcher salaries and everything. And it has like 175 billion parameters. This is like 365 gigabytes, the checkpoint only. So this is, I think human brain has pretty 80 million or something. It's like almost double, 80 billion or something, almost double the parameters. Bigger the better, of course, from their point perspective. And yeah, so you can see like how accuracy, how much there's a difference when you see when you see like larger networks, right? So this zero shot means you don't even fine tune, you just ask from the network. It's like this big Google but squashed into the parametric space. So then the problem is like how we can um, we can kind of compete with them, like how independent researchers can compete with them. Again, it is also really good. So for example, this GPT-3, I think it won the best paper award in NeurIPS or NeurIPS 2020 or something, that means it is a legit thing. So I kind of want to talk a little bit about future of these models. So uh, like now the world is moving towards bigger and bigger models. Then sometimes practical scenario, like we need to make applications that kind of that runs on devices, cloud, because and everything. So I mean, this is you can't, right? Basically, you need to have, this is only the hard disk space. Just imagine how much GPU memory you need. So you need to have, then if you want this model and run in your business, you can't even, you need to have this specific GPU structure or the computer structure, because because I have seen only 32 gigabytes GPUs in my life. Like we have like 10, but they are like not combined together. You need to come up with different architecture. So then the thing is, sometimes people say, although these big language models know all the things, for your task, for your specific task, we might not need such big models, such everything. So one thing is called this knowledge distillation. That means like kind of you have your big network which been already trained, and then uh, you have your task specific network. You kind of try to transfer knowledge from a bigger network to a smaller network. It's called knowledge distillation. This might be another nice research areas, and there will be nice applications, especially if you are interested in running these things on device or cloud, and concepts like federated learning, privacy matters, those kind of concept. This might be a very nice thing, and I certainly like encourage you to go through. And this is really related to something I'm working on now, uh, like recommendations and questions. And there's this amazing pitch of a um, blog from Stanford AI Lab thing. So I really encourage you to read it. It's really good, very new, like it came out of October 5th. So I thought of putting it here. So it's called like how we could use these big language models for tasks like emotion recognition and stuff. But rather than trying to trying this black box type, can we use a retrieval? That means can we make sure these big language models can we make sure this big language model learn how to select some specific information from given set of data, and then use that specific information and predict your final task, or do complete your final task. It's more like you don't right now, most like usual ways, you have the black box, you input your data, and it gives the accuracy. But then this black box need to be trained a lot. Black box should contain all the memory and parameters. So the idea is like, I'm again going back to GPT-3. So this GPT-3 being trained on trained on large amount of text prior to 2020. So if someone asks who won the T20 Cricket World Cup in 2021 or something, this network might not have that specific knowledge, right? Because then it's like again wastage of money, because you think, okay, I can create this large amount of brain, but that brain can't get updated because they call it your tool. That means you only train once, because there's no way other people can spend 12 million or something. So yeah, so this concept is what they say is, no, just go with a normal language model, not that expensive one, but make sure that language model can pick you can pick specific information from a given pool of information, then like use these things only, then predict it. So in this kind of, according to them, they call it, their idea is like retrieval is all you need. Like can language models train on retrieval task first, then use them to recognize emotions or recognize summarize content or answer questions. Yeah, I mean, I just put this stuff. I know I did not go through this stuff much, but I just put this stuff. Maybe if you have time, just go through and you will get some ideas about this stuff. And yeah, I'm really happy to um, answer any questions regarding this stuff later or today or anytime. You can always ping me on email, or yeah, email would work, or just even I'm pretty much okay even if it's on Messenger, so it's fine. Like yeah, so that's all for today, and uh, I'm really happy to answer if you have any questions.
Hello, can you hear me?
Yes,
Yeah.
yes.
Yeah. So
Good, yeah.
I have a couple of questions actually, and thank you, first of all, thank you for that very informative talk, and thank you for sharing those kind of links with us, which is really helpful. And I find this quite exciting for two reasons. One reason for the when you consider computer engineering seminars, this is the first time we are talking about self-supervised learning. We talked about multimodals and learning with different modalities. When we talk about learning with omics and images in this computation biology domain. But this is the first time we are talking about self-supervised learning. That's very exciting. And the other reason is it's been done by one of our alumni, which is really nice. So it's great to see the work that's been done by you. And I was just wondering regarding, so one thing, when you say fusion, what you are trying to do is, I think we are kind of trying to stack up neural networks on top of each other. And it looks like a huge task, which requires a lot of, I mean, in terms of the training, it involves, how are you going to be, if you think about gradient descent, you are going to do a lot of that here, isn't it? That is what it makes a lot complex. So in terms of training, how complex that is, if this fusion?
Yeah, so I mean, yeah, that I mean, I'm really grateful that you came up with that question. Actually, that's one thing I missed, because when I was doing these slides, when I was doing this slide, I wanted to add this part, but I somehow forgot. So yeah, that's a very good question. So when it comes to neural networks or deep learning, we always talk about this hyperparameter tuning thing, right? Like it's a fuss, and of course, as Dr. Heron mentioned, when you have like three networks working together, and you need to do gradient descent and like back propagation, we might come up with all sort of problems, because what should be the learning rate, what should be the batch, if you use normalization, what should be the normalization, should we use decay, or should we use warm-up updates, something like that. But the good thing of this use of I'm kind of directly going to this one, because nowadays you just use transformers, just use transform architectures, because this is like ubiquitous and it's really good. And when it comes to transform architectures and any self-supervised models, I'm talking about things happen like the recent one and very established models. You actually don't need to think of the optimization a lot. That shows the stability, because these things have trained for weeks and with billions of data. And of course, I'm pretty sure Google, Facebook, they do their own hyperparameter tuning and come up with these parameters. So that's why sometimes they say, although you have these codes, you would never surpass the Google's accuracy. You know what I mean? Like even if you train one of this network by your own, you can't get the Google's accuracy, because they might use different hacks, right? Because I mean, fine tuning can be from software perspective, you can use different hacks. But the good thing of these things when you are using for downstreaming tasks is they are like really stable. You actually don't need to worry about much of stuff. Like for example, as a practice, we use very low learning rates, like 10 to the power minus 5, like, or 3 into 10 to the power minus 5. That's like less like the norm, like, you know. So, and then guys, if you guys using from PyTorch, please move to PyTorch Lightning, just amazing. And I first worked with TensorFlow in my master's, then I moved to PyTorch, and now I completely moved to PyTorch Lightning for last 1 year. It is amazing. And these new software frameworks are kind of, they have this optimized structures or optimized framework types for fine-tuning these big language models also, because that's the entire point, right? You should not mess the knowledge inside these big neural networks by trying to do different hacks. And then again, nowadays we don't need to write our training loop like good old days. There are like different hook functions like trainer, data loader, and everything. They kind of pretty much optimize. But theoretically, answering your question, because of the stability, you don't have to worry much. So the rule of thumb is with if you use low amount of learning rate and some warm-up updates, we call like 500, it kind of works. And also when a big company kind of outsource these networks, they usually say if you want to fine tune on any downstreaming task, use this learning rate, something like that. And then again, there are frameworks like Hugging Face. You might have heard of it, because I kind of work a lot with it, and even we did some pull requests to them. So when you're using them, you have this standard procedure, because it doesn't matter what is the task you are doing. End of the day, it is a downstream task, so you kind of can use it. So yeah, that's like one plus point of using self-supervised learning. You can save a lot of time about going through hyperparameter tuning, and you actually, in experience, I have never faced any gradient overshoot or training instability. I have trained like quite a few self-supervised learning models. Like I'd say, I mean, even testing wise, different models, like so many, but I have never came up with these issues of overshooting or NaN loss or anything, unless or otherwise the task itself is super hard.
Right.
Did I answer your question correctly, or?
Yes, exactly. That's what I was, wanted to clarify about. And I have two more questions. And it's also interesting that when you consider about natural language understanding, so we started with the statistical methods, and we kind of went to the neural machine translation methods, and it looks like now we are in the self-supervised learning era. And I was wondering whether, I think you briefly touched on it, are you considering about learning between modalities? So are they going to be interconnected?
Yeah, that's a very good question, because I wanted to do this pet project recently. It's about, because I'm really in love with these days about question answering and machine recommendation and search kind of things. So I wanted to try it's a good area to actually work, like multimodal question answering. Let's say sometimes we need different modalities, right? Let's say you for best example is medical domain, right? You have some doctors, prescribe doctor some comments or something, and maybe there's an x-ray, right? How we can so you have a model, and you need to input that x-ray image as well as the doctor's like what are the domain experts description, and you need to make sure. So so I was thinking actually it should be better, because if we kind of if we kind of come up with the mechanisms that that works independently, like, because then you don't have this legacy element in your code, right? Because the entire idea is this Bert or now Robert or these models gonna change. So that's, so you can't, so I'm pretty sure by when if I join industry, and then even now there might be better models than this. So every year Facebook, Google, they are not going to stop, right? They will, this is our checkpoint, so you just need to plug it, right? So in that way you can use like, rather than like, you can use like this. But again, I've seen this Google block. It's not open source. Google did not open source the model, but you can check. It's called I don't actually multimodal thing, but the idea is they are working on training a big neural network, self-supervised neural network, that works with speech, vision, and text. And there are already models that can work with text and speech. That means your model can take input. That means not this is not like two models, but sorry, text and vision. Like for tasks like visual question answering, like you have you have an image and you have a question, and then there are model, like one single model that could take text as well as the image, like
Yeah.
the features of an image. So usually their pretext task is like combination of this. They use the mask language modeling for text, and then they use things like, you rotate the image a bit, right? Then you need to rotate the image a bit, then you need to predict the rotation angle or something like that. Or maybe actually you now it's been proven that things like, you divide your image into sections, and you mask out one section, and kind of ask neural network to identify which section is masked out, because everything has because you can use now, it's you can use transformers for vision also. So it's because of, since this network architecture is becoming ubiquitous, people are kind of now trying to train trying to train these one big models. So there are several models that could work with vision and text, but I am yet to see. But I saw this Google thing. They claim they have this big model which could take all these three modalities, and I think they have not they are not going to open source it, because it's from Google business blog, and then they are going to plug it to the search, of course. They won't open source it. But yeah, so both of research fields are actually actively working on that. But I think honestly, rather than there will be like people will be like these big companies will mainly open source models that could input. I mean, there are already few of them, and work with both text and vision and other modalities together. Yeah, with the time.
Yeah. So I'm guessing if we have something like that, for example, I can talk to a bot and ask, how long should I take this medicine for? And whether I should
Yeah,
continue this medicine,
exactly.
and it can
Yeah.
analyze a text prescription from the doctor, and also maybe check an image of my previous record, and then it can recommend me something like that.
Yes.
I think
Yes, because
hypothetical scenario. Yeah.
it's pretty much it. Yeah.
So one last question I have is that these languages that we are thinking here, so I'm assuming that most of them are on English language. So how applicable they would be when they come to Sri Lanka for us in a local context?
That's also, so these transformers. So I can give you some examples. Like actually there are a lot of multilingual transformers. That means I mean main use case should be machine translation, right? Like, I mean, main thing, because like, let's say like this. I mean, this is like a funny context, because sometimes how I would see is, for countries like us, like Sri Lanka, let's say we have 20 million people, right? So for me, it would be better to have good machine translation mechanisms, right? Then
Yeah.
you can always use
Yeah.
English thing, right?
Yeah.
So, but again, people then rather than like train, but you can actually there's a train version. I know there's a train version of BERT for Sinhalese. I know there's one of my friend in Sri Lanka called Keshan. It's basically he's working with Google I/O or something. I mean, it's like more like a business perspective way. So you can feed your own language and train it. But I'd say machine translation plays a huge role nowadays in the research, especially non-English things like French and stuff. So Chinese, exactly, Chinese, French, and yeah, I mean the problem with Chinese is they have their own Google and stuff, right? So they like Baidu has same copy of these models, and maybe they sometimes it works better than that, but not just training, but you can have like, for example, models like there are a lot of like machine translation models like Marge. You can check what is Marge. So it's also a transformer model, but what it does is it can work with English and other languages too, because some people kind of train with mix amount of mix of languages, you know what I mean, like, because then you can handle a lot of tokens, because language is more like how many it depends on number of tokens. For example, in English word we have 50,000 tokens nowadays, and in Sinhalese if someone tokenize this stuff, actually that my friend, what he has done, what his main thing is to tokenize, help them to tokenize the Sinhalese. In English, like tokenization means like, if you take this word, let's say environment, envir is one thing, then MENT is another thing, because MENT is common, right? So it could go along with other stuff. So what these transformers does is they might able to already train, they might able to already understand French, English, and some other Chinese, because they've been trained with multilingual context. Because one time you mask out a English sentence, other time you mask out a Chinese sentence, right? So you have a big probability distribution to predict, but when you have enough data and enough computation power, you can do it. Then if you use such kind of multilingual language model, I think the adapting normal English word to machine translation of Sinhalese compared to compared to using this multilingual language model might work better, because multilingual language model, somehow the model kind of surely knows how to work along with different languages and stuff, right? But yeah, so, and anyway, like most of current machine translation models also comes from transformers, like all these WMIT tasks. All these things are being governed by transformers, and already there are things, there are models that can translate. And I highly if you guys want to do this project and open source a Sinhala sentiment analysis or Sinhalese summarization model, work with Hugging Face. That's because it's really good, nice documentation, and if you have the right data set, you don't need to, you can train and everything. So Hugging Face, then if you go to their website, they have a model hub. You can see people have upload their models like about different languages, you know, like French, even these Hindi, Tamil, and those kind of stuff. Hugging Face, again, I'm saying Hugging Face model hub. Just go through it. It has everything, like they have, it's like the biggest open source NLP framework. You can use it for training, you can use it for inference, also you can use it for publish your checkpoints and stuff.
Yeah, in Hugging Face, I see 2 Sinhalese datasets. That's from Keshan, I think.
Yeah, Keshan, yeah, he was. You do you guys work with him?
No, I just learned it from you actually just now.
Yeah, because I also haven't talked to him in ages, honestly, so he might not even remember me. But when I was in Sri Lanka, we had this meetups, I think meetups, but yeah, I don't know now actually.
Thank you.
So, before I conclude this session, I would like to thank Mr. Shamane on behalf of the students and the computer engineering department for joining us today and sharing your knowledge and experience with us. I'm pretty sure your words today will boost the motivation of the students to step into the world of research and contribute at an international level. I would like to thank all the lecturers, especially Dr. Damayanti Hera, for initiating these computer engineering seminars and for organizing today's event. I would also like to wish you all the very best in all your research career and all your future endeavors. We are truly, truly proud of you and happy to see someone who was once at where we are today, now performing so well, contributing to successful research. Thank you once again, Mr. Shamane, and wish you all the very best. And we hope you will be in touch with us to share more knowledge in the future. And please feel free to give your feedback about this seminar using the link mentioned in the chat in order for us to improve the experience in the future.
Thanks a lot for inviting me, and yeah, this is like really good and I really enjoyed, and it kind of also I'm really happy, you know, I really miss Sri Lanka for last 4 years honestly, and that's not I've been kind of, you know, it's like a kind of a technical prism here because I don't know, New Zealand does not want to open its borders for some reason, and yeah, it's really nice. I actually enjoyed as much as you guys have done, I mean, hopefully. So yeah, thanks a lot, and please if you have any questions, if you find these topics interesting, just ping me up, and I'm really happy to help you guys too.
Thank you so much, everyone. I'm going to end the meeting. Bye. Have a good day.
Bye.